Can atoms finish a process before they start it? A new quantum experiment suggests yes. Quantum physics has presented scientists with phenomena that are difficult to imagine, such as particles that cross barriers and states that change when observed. However, the concept of negative time has always been particularly disconcerting. This new experiment could change our perception of this phenomenon. For years, many physicists thought that the results on negative times were mere mathematical artifacts. However, the recent experiment with ultra-cold rubidium atoms has reopened the debate, suggesting that this behavior could be real and observable in the matter. Scientists conducted an experiment where they sent pulses of light to a cloud of rubidium atoms. The results were surprising. Some measurements indicated that the duration of certain processes was negative, implying that atoms seemed to finish their interactions before they had begun. To illustrate this phenomenon, you can imagine a ball passing through a tunnel and leaving before it took the necessary time to cross it. Although this analogy is not perfect, it helps to understand the strangeness of the experiment and the results obtained. The most interesting thing is that researchers were able to ask atoms directly how they responded to light. Using weak measurements, they managed to observe how rubidium atoms reacted without completely destroying their state, which allowed them to obtain valuable information. Unlike previous studies that depended on indirect interpretations, this experiment is based on direct observations. This makes the results more difficult to ignore evidence and opens up new avenues of research in quantum physics. The term negative time can be confusing. It does not mean that time goes back or that information can be sent to the past. This phenomenon manifests itself on quantum scales and is related to the evolution of certain states during ultra-fast interactions. In classical physics, measuring the duration of a process is relatively simple. However, in quantum mechanics, things are much more complicated. Particles do not have defined trajectories, and processes occur in state overlaps, which makes questions about duration puzzling. The photon was not absorbed conventionally, but still altered the behavior of atoms. This finding suggests that even processes that do not end as expected can leave measurable physical footprints, which challenges our intuitions about cause and effect. Modern physics has come a long way in understanding particles and waves, but the concept of time remains a subject discussed. This new experiment could reopen old scientific discussions and bring us closer to a better understanding of time in the quantum context.